advanced in handling non-ignorable non-response. Let's welcome Dr. Shao.
Thank you, Yang. I wanted to thank WSS for arrangement of this seminar, and this research is partially supported by NSF program, EMS, and MMS. Trying to see. It's not moving. Okay. So here is a quick outline. After some introduction, I will concentrate on two major pieces of some kind of recent work. I will talk about the dimension reduction and the instrument selection, and in that case is the first case is the semi-parametric propensity case. And then after that, I will also talk about the model variable selection in semi-parametric pseudo-Lexhold approach. So to start, let me just introduce the problem with the simplest case, where we only have one univariate response variable. The notation is y, and it is subject to non-response. And we have a covariate vector x without non-response. And then delta is just an indicator of the whether or not the y value is observed. As I said, this is the simplest case. More complicated cases are where y itself could be multi-dimensional, or x itself has some kind of missing value. But for this presentation, I will concentrate on this special case. So as we know that statistical inference based on the joint distribution of these three components, y, x, and delta, and it can be decomposed in certain ways. And this one way is decompose the joint distribution in terms of the conditional distribution of delta given x and y, and this is the so-called propensity. And then the conditional distribution of y given x, and so on. And typically, we are interested in the distribution of x and y, and non-response is just a nuisance. However, especially in the case of non-ignorable non-response, actually the propensity plays an important role here, and although it is a nuisance parameter. So first, before we talk about non-ignorable non-response, what is ignorable non-response? Ignorable is simply missing at random in this case. The assumption is that the propensity actually doesn't depend on y, only depend on x. And because y is univariate, so in this case it's pretty simple. So this assumption that given x, the propensity only depends on x is the assumption of ignorable non-response. And for that case, actually, there's a huge literature. So if missing is not at random or non-ignorable, then that means that the propensity, the y variable cannot be excluded from the propensity, even given the entire x. So this is a difficult kind of a situation. And actually, in many cases, the reality is that the thing is not ignorable. The main difficulty in this problem is that, first of all, if we don't handle it, we just treat it as if it's missing at random, then of course what the estimates and the inference will be biased. The major difficulty is that without any assumption, actually, because of the non-ignorable non-response, some parameters in the population is not identifiable. It's not like the ignorable situation where originally if the distribution is identifiable, then with ignorable missing, the distribution is still ignorable. Still identifiable. But non-ignorable situation, we cannot estimate some of the parameters if there's no further assumption. So one kind of assumption to identify the propensity and also the model is that we assume that some part of the covariance is actually not related to propensity given all the others. So here the notation is that I write x is equal to x can be decomposed into two pieces, u and z. And here z can be excluded from the propensity when y and u are present or conditional. And here I just write a simple notation, x equal to u and z. It sounds like u and z are components of x, but in general, it could be just some functions of x. As long as the two functions put together give you back the entire x. Okay, so could be functions. So this is the assumption that I'm going to make under the non-ignorable non-response. And the motivation is that if we don't actually exclude any of the variables from the propensity, then the problem is not solvable. It's basically because of the if both y and x have to be in the propensity, then there are basically too many parameters, and we cannot actually identify all of them. So if some of the variables are not there, then the model will become simpler, and therefore it's identifiable. So under missing at random, actually it just simply says y is not there. That makes the model actually a lot simpler. But if we say actually it's non-ignorable, so y cannot be excluded from there, then the next thing you think about naturally is some of the covariance can be excluded. That will also do it. You simplify the model, and therefore we can actually get something going. Without any kind of assumption, then it's harder to do anything. So now I will turn to some existing work, the work before the presentation of my work. So suppose that we do have such a variable, and I call this variable non-response instrument, or simply called instrument. So the first assumption is that z can be excluded from the propensity. Actually, there is another thing we need to assume on z. That is the original density of y given x should be a function. Actually, should be a function of z. If z can also be excluded from this density y given x, then it means actually Z is totally just garbage. It doesn't relate to response and doesn't even relate to the y value given all the other covariates. Then this covariate simply is useless because of the if the other variable u is present, then Z can be totally removed. So we actually need to assume that it can be excluded from the propensity, but this variable cannot be excluded from the joint density of y and x. So then this Z will be useful. Okay, so this is the definition of instrument. So an instrument is not only kind of can be excluded from a propensity, but also it is a useful predictor of the y. Okay. So in the first kind of work related to this idea is we assume that an instrument is given. So from the covariate, you kind of know this covariate is an instrument. That means that it is not related to the propensity, but it's related to the y value. When I say not related, it's always conditional. Okay, conditional on other covariates. And still, we need to make another assumption on either the propensity or the conditional density of y given x. That is, we have to assume that these two pieces has at least one parametric component. If they are totally non-parametric, in other words, both of them are non-parametric, then actually the entire problem is non-parametric, and we actually have counterexamples. This cannot be done. Of course, you can make them both parametric, but that is usually kind of not very robust, especially when we have missing data. So that actually leads to two kind of tracks of work. One direction is the first paper published by Tang et al. In 2003. They actually kind of use a pseudo likelihood and assume that the propensity is unspecified, but the joint density or the conditional density of y given x is parametric. So then this will be also, I will also address this kind of direction later. The other direction is actually 2002 by Qin et al. And that one is totally kind of reversed. This direction assumes that the propensity is parametric, and the conditional density of y given x is unspecified. And this work actually can be improved. One of my own paper in 2016. We actually don't need to assume propensity is entirely parametric, as long as there is a piece actually is parametric in that density. In that propensity. So here is a more close look at what has been done. So we are going to assume propensity has some kind of form. And this first line is that something like the odds is equal to a product of a function of x and then a function of y. And here, the function of y has to be parametric. So there's a gamma there. So this q, y, gamma is a known function if gamma is known. So that part is parametric. For the covariate part, gx, totally unspecified. So G is non-parametric. So after we assume this kind of propensity, this is a semi-parametric. A kind of a key result is that we can actually estimate the conditional expectation of Y given X and for the non-response, delta equal to 0. And that one actually can be expressed in terms of the quantities that it is observed. So you see that the far right-hand side of that equation actually, there's always a multiple of delta in there. Delta is equal to 1 and it's observed. So that quantities are all observed. So because of that, actually, a paper by Kim and Yu in 2011, they first assumed that this gamma 0 is known. In other words, actually, the parametric part actually is known. Gamma is equal to gamma 0. And once we have that assumption, then this part can be estimated. Because once gamma 0 is known, then that's why gamma 0 is a known function. So once we observe the Y and then we use the observed data, that we can estimate unknown conditional expectation. And therefore, afterwards, we can estimate the population mean. This is the theta hat given in the last slide. However, assuming gamma is known is almost like the same as you have to assume that you have some kind of external data to estimate the gamma. Somehow you can estimate this gamma beforehand. Otherwise, I don't think in any practical situation gamma is known. So the contribution of my own paper in 2016 is that we get rid of this assumption. We don't need to assume gamma is known. We actually go on to estimate gamma by using estimation equation or the method of generalized moment. So here, after we estimate the gamma, then we put a gamma hat there, and then the last line theta hat is the one that after we get the gamma hat. Once you observe, once you have an observation and estimate the gamma by gamma hat, then we can almost like treat it as if it is known and put it in the to replace the gamma 0, and then we are done. So far this is just a review of what has been done up to 2016. But there are two issues needed to be addressed. Actually, I have two issues here. The first issue is not so crucial. The first issue is just based. Sometimes maybe the dimension of this variable u is high. So if you look at the in the middle, I have this g hat gamma u. That's actually an estimate of the non-parametric part of g. It's a function of u. It's a non-parametric. So we use kernel. And if u has we don't have to have like a very high dimension. As long as I think U is something like a 5-dimensional or 6-dimensional, there are some trouble to use the kernel. So that's one thing probably needs to be done. The other is more importantly is that so far the previous work always assumed that a Z is given. So that means I actually know which variable is also related to propensity. Okay. So the next to use the so-called sufficient dimension reduction to actually solve this problem under some assumption. For that purpose, I will briefly introduce what is sufficient dimension reduction. It is totally a non-parametric method. It's almost like, at least to me, it's almost like started with, we wanted to do variable selection or model selection non-parametrically. Right? We know that there are many kind of parametric model selection and variable selection. Even Lasso, they are partly, you have to have a parametric component. But if we wanted to do things totally non-parametric, then that's the sufficient dimension reduction. So what it does is that I put it here. You have one spore, and that is called a Y, and you have a covariate, which is called an X. And typically, Y is lower dimensional. Let's just say, assume Y is equal to one-dimensional, and X is high dimensional. So the sufficient dimension reduction says that I want to find an S, which is a linear function of X. So it's B times X, where B is a matrix, such that the dimension of S is smaller than the dimension of X. And Y is independent of X given the summary S. Okay. So that's actually important. It means that given S, then the rest of the X is not useful in terms of predicting Y. So after that, we can use a lower dimensional S to replace X. Okay. And the sufficient dimension reduction is simply some kind of a way to estimate this B, right? So let's assume that such a B exists. And after that, you still have to estimate. You cannot say this is B is given, right? So the whole literature of sufficient dimension reduction is just there are so many methods that tell you how to find such a B. Okay. So we call the BS. But now, our problem, how do we actually do the sufficient dimension reduction when we have missing data and also the missing is non-ignorable? If missing is ignorable, then I don't think I need to talk too much, because ignorable missing means given, what is observed, that distribution is the same as the distribution that is not observed, right? So therefore, you simply do the sufficient dimension reduction in terms of the observed data. Once you find such a B, that B is also good for the other part, and therefore it's also good for the general. So there's no issue. But the non-ignorable situation, we know that actually these two distributions are different, right? The one that the delta equal to 1 and the one that the delta equal to 0, they are different. So if you do sufficient dimension reduction with the one that the delta equal to 1, after you find that B actually does not apply to the other part of the distribution, and therefore the problem is still not solved, right? So how do we actually do sufficient dimension reduction when we have non-ignorable missing data? So here, actually, my original goal is to find the instrument, but I found that in the same way, actually, I got both of them. In other words, one is how do I do sufficient dimension reduction when we have non-ignorable missing data? Second, how do we identify an instrument? So this is the new methodology. dimension reduction and instrument selection. So the assumption we have is semi-parametric propensity. So that's the assumption. Our work actually is based on the following two key identities. So under this assumption, we can actually derive two identities. And that two identities are in the middle of this slide. One of them says Gx is equal to right-hand side is some kind of expression. Right? But the key thing is, okay, maybe I'll talk about the second equation actually is also important. What is the second equation? It says that the conditional density of y given x when delta equal to 0 is equal to the conditional density of y given x when delta is equal to 1. And after that, you have to multiply something. Okay. And that something actually depends on delta and also that Q function. It's all from that assumption we have. Okay. So after that, you look at these two identities. Then quantities show up in these two identities are three quantities that I listed below. One is the probability density of y given x when delta equal to 1. The other one is the conditional expectation of delta given x, which actually, because delta only equal to 1 or 0, it's actually the probability of delta equal to 1 given x. That is not a propensity. Okay, the propensity actually has a y. So this one is simply you actually integrate out the y, then it's some kind of function. And the third quantity is the conditional expectation of delta times this Q function and given x. So the previous three identities actually are decided by, I shouldn't say actually are decided by these three quantities. The quantities involve x are all in these three quantities. If you look at the first, Gx actually is a ratio of the second one and the third one, right? And the conditional density of y given x, delta equal to 0, is equal to, there are actually four quantities here, but one quantity has no x in it. Only three quantities has x in it. And that are the three quantities in the last line. Why the quantity without x, I don't have to pay attention. Remember that here I'm doing dimension reduction with x, right? So the one that is only a function of y, actually I don't need to worry about it. So if I wanted to do dimension reduction, if you look at the expression of conditional density of y given x and delta equal to 0, that piece, how do we do dimension reduction for that piece? Well, because this piece equal to a function of three pieces that are listed in the last line. So if I'm able to do dimension reduction on the three last pieces, then I'm done, right? See, the only thing is I want to find a function of x for which the left-hand side only depends on that function. Now, if I do it one at a time, these three pieces in the last line, if I can find some kind of a smaller set of x such that the first one is only kind of depending on this, and the second one is dependent on another one, and the third one is dependent on another set, then I can simply pull this together, and that is a combined set is the one that I'm looking for. Hopefully that their dimension is not so large, so that when I combine them, it's not a huge set. Right? So that's actually the key motivation of our work. And the next, I'm just doing it like I said. Okay? I'm going to do dimension reduction in 3 steps. The first step is actually related to the first quantity in the last line. That one actually is easy. It just says, okay, for delta equal to 1, those observed data, I'm going to do a dimension reduction using the existing methods to find a B1 times X, such that given B1, Y and X are independent. And that one, actually, this B1, if it's ignorable missing, then that B1 is all we need. Right? Because if we have an ignorable situation, under my assumption, ignorable means what? Means that this Q function is constant. Doesn't depend on Y. Right? And therefore all of the things cancel. And then the two densities in the third last line, actually they are the same, and that factor is actually equal to 1. So the first step actually is just, if you have an ignorable situation, then you just do this. Second, I'm deal with the second quantity, which is delta. So I'm going to find a B2 such that B2 times X, given B2 times X, delta and X are independent of each other. And this is also durable because both delta and X are observed. X has no missing data. The third one actually has a little bit of trouble. I needed to find a B3 such that given B3 times X, delta times Q are independent. This quantity is independent of X. Where is the trouble? The trouble is gamma is unknown. Right? If gamma is known, then there's no trouble at all. These are all observed, right? Because delta times Q. So I either get a 0 or I get just Q. Right? So how do I overcome the difficulty that gamma is unknown? Fortunately, there are some kind of shortcut. Suppose let's take an example. Suppose that this Q Y gamma is equal to exponential of gamma times Y, and that one actually is a model actually proposed in King and Yu, and that's a very common assumption on this kind of model. If that is the case, what I can do is that I fix a value gamma 1. That fixed value is not necessarily the true value. Okay? True value is gamma 0, which is unknown. So fixed and gamma 1, then any gamma actually can be expressed as a function of involving gamma 1, and then there's also a gamma. Okay? So what I'm actually do is, if that is the case, then I will treat the gamma 1 as a kind of a special value, and I'm going to find out the set B3 using that gamma 1, although gamma 1 is not the true value. But if any other true value of gamma can be expressed in terms of a function of gamma 1, then I'm going to make use of the important property of independence. In other words, functions of independent variables are still independent. here, the next proposition is a more general situation. I'm going to assume that the gamma, the Q function, Qy gamma, actually can be expressed in terms of maybe R base function. Okay. Here in the top example, actually R is equal to 1. But you may have a more complicated model, right? It's not just exponential of gamma times y. I mean, you could have an exponential gamma times y times beta times y squared or something else. And in that case, the function can be expressed in terms of several different known functions. Each of them, I fix a gamma. And that is not necessarily true value, right? Because I don't know which is true value. So if my function, the parametric function, can be written in this way, and where precise sub gamma is just an arbitrary function, it could depend on the parameter gamma. So if B3 satisfies given B3 times x, delta times this base function are independent of x, then I'm done. Because the real Qy gamma is a function of this thing. So as long as I find a B3 such that the condition on B3 times x, they are independent, and functions of them are also independent. Therefore, this B3 actually doesn't depend on gamma. It depends on the initial value I choose, but I think that they are all equivalent. It doesn't matter what values you choose. Okay, so after that, the second last line here is just says, okay, so I found the B1, B2, B3, right? So I'm going to just take the linear subspace of all these three subspaces generated by these three matrices, and I use this notation plus. This circle plus means it's a linear space. Add together the linear space. If B is the base of such a linear space, then I indeed find a B which is, has the property that given B times x, y and x are independent of each other. So this solves the sufficient dimension reduction issue. But my purpose initially is not kind of just wanted to solve the sufficient dimension reduction. Right? My initial purpose is trying to find the instrument. But I found that actually, instrument becomes a byproduct of this whole thing. Normally, when people do sufficient dimension reduction, they try to get rid of some covariates which is not useful. Right? A linear function of x, it could be almost just described as a subset of x. So you try to get rid of some of the linear combinations that they are not useful. But for my purpose, actually, I do one thing and get two pieces of results. In the sense that not only I find a B which says that, okay, these functions are useful, but also the not useful part is actually candidates of the instrument. What is an instrument? Says that it's not involved in the propensity. Right? So if we go back to look at this function, if you look at this G function, that G function is the part that the non-parametric part of x, right? So if I wanted to find an instrument, so suppose that in the end I found a subset of x such that the G only depends on that subset, then anything not in that subset is actually a candidate of instrument. why do I say it's a candidate? It's not actually, because I still need to find one such that it actually can predict Y, right? Remember that if they are all useless ones, then I still don't find an instrument. So after that, I needed to do one more thing in order to find my instrument. So this slide sounds kind of complicated, but maybe when I explain it, it's much simpler. So remember that for the G function part, I will already have something which is not in the propensity. The only thing left is I wanted to choose some function of it. It actually depends. Those functions can predict the Y value. So I first use this orthogonal space. So suppose A is the space that actually generated by matrices B2 and B3 that are previously given. Then A orthogonal is the space that contains all the vectors orthogonal to A. And after that, I'm going to do one more thing that actually I'm going to remember that previously, what is B1? B1 is the one that, the first step. B1 is the one that all the covariates that are related to Y, right? And the B2 and the B3 are actually about the G. So B2 and the B3, that put together, that's a kind of something like a they are functions that is related to propensity. So anything in the orthogonal space of it could be a candidate. And the B1 is the one that actually related to Y. So how do I get the instrument? I just simply project this B1 into the orthogonal space of B2 and B3. That will give me a vector, that at least one vector that is actually satisfy both requirements. And of course, in here, I assume there is one exists. Okay. Otherwise, if there's none such thing exists, then you may end up with empty. Right? E1 is probably, you project it to that space, actually you don't get anything, only zero. So under the assumption that one such instrument exists, then I should not get empty. So that actually finishes the entire work. And here I have some simulation. So this simulation is just, we have several different models. And originally it's a 10-dimensional X. And then some of the X actually doesn't. If you look at the model A1, A2, A3, and so on, they are modeled for the response Y. And the model M1, M2, etc., they are the model for propensity. Okay. So some variables are actually related to propensity. Some variables are actually related to the value of Y. And then we just use our proposed method to search for an instrument. And also, actually, we also get a dimension reduction. So we actually apply the simplest dimension reduction method, the method so-called SIR. That SIR actually is slice inverse regression, the oldest dimension reduction method. And here is our simulation. So after the dimension reduction, then we actually follow the previous work to construct our estimate. And here is the simulation. Just shows that the method works fine. There are some details, so I'm going to just omit them. And here is a data example. It's about a study. It's it's an older data set. We applied, actually previously we also applied our method to this data set, but at that time we assumed the instrument is known. So we actually picked one instrument. But here we actually use the new method to search for instruments, and in the end, there are 4 arms of this article. So that is 1, 2, 3, 4. We just do it separately within each arm, and this table, the instrument X1, X2, X5 for the first arm is selected to be instrument according to our method, and so on. So you see that there are some differences, but the X1 and the X2 are always in there. X1 actually is the age, X2 is the weight, and X3 is the CD4 count at the baseline, and X4, X5 they are CD8 count at the baseline and 20 plus kind of a week. So you see that X1 and X2 are age and weight. What are the instruments? The instrument is the one that does not, given all the other variables, they are not quite, useful for predicting whether you respond or not. So what I learned from this problem is that for count, they are missing is simply because the patient is too sick. So therefore, CD4 count at the baseline and the CD8 count at the baseline and the 20 weeks, they are very good predictors of whether this person will missing the data or not. Given these variables, age and weight are not really important in terms of predicting whether or not this person will be non-response. However, they are still useful for the entire predicting of Y value, the CD4 count. So that characteristic is exactly the one that we want to looking for. So no wonder we always find the X1 and X2, they should be included as instruments. And sometimes the X3 and sometimes the X5, they could be, that's the CD count in some other situations. Okay? So, but not all of them, because sometimes it might be like given one of them and the others are not other predictors of the missing. Okay. So now I'm going to switch to the second approach. This part is shorter. So don't worry. I saw you. I was looking at the time. So the second part actually just says it's the other way around. Let's assume that the propensity is totally non-parametric, and the joint the density of Y given X is parametric. So then, using this last equation, that's kind of like a Bayesian formula, can actually, if we know beforehand D is the instrument, then we can use this to solve the problem, to try to estimate the parameter in the density. So here are some of the details about how you actually estimate the parameter theta when we know D is an instrument. But I wanted to just briefly talk about the model selection and the variable selection. So similar to the previous problem, the existing work are all kind of like assumed how do we actually select a Z? And this time is a little bit different from the previous work, because previous work there is an assumption for the propensity, and right away we get some identities which will help us to find out, which X is useful or not. So for different quantities, in the end we solve the problem. But for this case, we actually don't have anything. So propensity is we don't have any assumption. We only assume there is an instrument. That instrument means that it can be excluded from propensity. But otherwise, we cannot use propensity. The only thing we can use is the parametric density of y given x and some kind of beta. So our proposed method is use this to build on some kind of estimate of the density of x, the covariate x. So because covariate is always observed, and therefore we can actually estimate the density or the distribution function of the covariate. Then once we assume one variable is the instrument, then we can actually have the pseudo likelihood and supposed to get a better estimate of the joint distribution. So we're going to use this idea. Just try all different kinds of Z's. If the Z is a wrong instrument, it is not an instrument, then the estimation will be really bad, and therefore, in the end, it will be far away from the empirical distribution. Because to estimate the distribution of x, without any model, we can simply just use empirical distribution. So empirical distribution becomes a standard. If I fit a model with a particular Z, and then I compare it with the empirical likelihood or empirical distribution, and if their difference is small, then I try to believe that this Z is if the difference is large, then I will eliminate that. That's not what I'm looking for. So using this idea, we have some initial results. That actually you can search for a Z. But all the work so far is for really low dimension. And with that kind of thing, you see, you try all different models. I mean, if the dimension is high, then it's not a. So there are kind of we are still doing research in this direction. How do we at least handle the situation where the covariate is something like a 10-dimension? I mean, we probably cannot handle the dimension to be 1,000 or 2,000, that kind of thing. But at least a method that can handle 10-dimensional covariates. In many examples, you have something like 10 covariates. That's not unusual, right? So here are some details, but due to the time constraint, I'm not going to talk about details. So we have some simulation results similar to the previous situation. So here, kind of like we have five models. 5 models actually says that that's the joint density of the conditional density of y given x, and then we try to search for an instrument using this idea. Some kind of simulation shows that when the sample size is large, then the probability of hitting the right target is actually pretty good. And actually, we also need to put some penalty in the. You know that if the models are nested, then you could have something like a 3-dimensional a 3-dimensional variable is an instrument, But if you throw away one of them, two-dimensional, it's still an instrument. It still be used. But then it might not be as efficient as using all three of them. Right? So we need to put a penalty on the dimension of the other variable so that we can have as many as these components of these as possible, and that will give us a more efficient result. So because of the time constraint, I don't think I want to go through this example. This example actually is actually about the fixed Z. So okay, thank you.
So in theory, we have to have the instrument that is completely independent of the propensity, but also predictive. In practice, we're probably going to find something that might be a little bit predictive of the propensity and somewhat, and hopefully more predictive of the thing we're interested in. Which is so if I was deciding on putting a variable x11, x10 in there or not, is it better to have one that's more predictive of the propensity or less predictive of the, did I say that right? Or less predictive of the variable of interest?
I see what you mean. Actually, I have to admit that this is not kind of like this work is not complete. So some of the questions you raise maybe when we do some examples, you will sooner or later run into such kind of problem and say which one actually I should use. And also there's efficiency against robustness kind of thing. I mean, if you want to be conservative, then you just get one variable which is instrument. That would be enough to entirely solve the problem, and possibly you are robust because the chance that you make a mistake is small, right? You just pick one of them. And on the other hand, suppose you actually have five together, five of them are all instruments, and you just use one of them, very inefficient. On the other hand, if you include all five of them, the chance that you make a mistake is larger, right? Any one of them can be, a fake one, so that then you run into problems. So those kind of study, I admit, is not complete. We're just get some kind of initial result. It shows that there's a hope that you can actually just use data to search for instruments instead of kind of say that okay, you have to give me an instrument, otherwise I don't do the work. So especially the second part, I think it's not completed yet. But I hope at least some ideas are kind of interesting, and this is just kind of initial result.
Yeah, so in all of this, we actually know that non-response is not ignorable. Apparently, there's a proof that anything that is not ignorable non-response is bound to be better than ignorable non-response. But you say that the data can't help. Agree with that or not?
I heard some of these kind of arguments. My approach is kind of like you start with an assumption, and then if this assumption holds, I mean, my first piece of work is that assuming that the propensity has this kind of the ratio, odds ratio is equal to some kind of thing. If this is correct, then whether or not you have ignorable is just because just that Q function is a constant or not. It depends on y situation this is not a constant. But if that one is a constant, then I'm kind of like doing something for nothing.
You still never know.
Yeah. But
it always struck me that you just use sense about the nature of the data.
yeah.
In some cases, it's obvious that non-response has a function of an observation, not a.
But for the
I don't like the term instrument variable only because it has to do with form and function. So I use the term shadow variable. More naturally, shadow variable. This makes more sense to say non-responsive. Example I said, we work in survey, so it makes more sense to say that non-responsive is a function of your income rather than the income of people in your census block. One makes sense as an instrument, one makes more sense as a predictor.
I think there are multiple responses to your question. First of all, I think regardless of what you call it, I call it instrument. Some other people call it shadow variable, and maybe there's some other name. I hope our approach actually shows that, for whatever things that people define, we have a way to try to search for it. It's not necessarily always have to be given. Actually, maybe 3 years ago, if you ask me that question, my answer probably is, that one is too difficult, has to be given. But now I found that at least, under some situations, you can search for it. The second response is that, with the question earlier, we talked about ignorable and so on. Very likely, if we try this in an example, and actually the response is ignorable, I think sooner or later you will find it. When you do this, and you find that actually, they are not so useful. They all give you the same thing. Then you stop it. You say, okay, this data set actually is ignorable. We don't have to apply such kind of technique. And only when you really have a non-ignorable kind of missing data, then you try this, and you find out they are all different. Because if it's ignorable, then it doesn't matter which one you call it is instrument, right? I mean, they will all give you the same results. And I would say, well, how can it be so easy to find an instrument? Well, that's because the data is ignorable, so you don't have to do it, right? So I would think that, this kind of a theory is just some kind of a guidance. What do you need to do, and in the end, probably you still need to use your experience, and it just says, oh, actually, it's something else needed to be done, not actually just this. And finally, I think that, as I said, my approach is always like there are some assumptions, and then that kind of like one assumption is the form of the propensity, and the other assumption is hidden there. It just says there is an instrument. I mean, if that is not true, then whatever you do actually turns out not actually correct. Right? Suppose we indeed have a problem where things are not identified. It's actually whoever is doing it is not going to be a good job. And then I'm going there and I find that probably this one is the instrument. It's still wrong. Right? Actually, there's no instrument. So I just hope we don't run into that kind of a situation.
Any more questions? Which might not have. All the stuff you collect the data on are predictors.
There are some kind of questions I think deserve the further investigation. For for example, maybe the normal comes from that you didn't measure some of the covariates, right? And that covariate, if you include that in there, then it's ignorable. If you don't measure that, that becomes a confounder, and that is the cause of non-ignorable missing. If we have this kind of situation, maybe we should do some research under that situation and find out something. And that is not the framework that I'm talking about.
The perfect particular why that I have to worry about.
Let's ask any question from people on the phone? Here, I have one question.
I think I agree with what you said. Because if you actually have a situation where actually you know there's certain structure, then you probably under that kind of situation, you don't need to do what I have just presented here. So, for example, if you say, okay, the non-ignorable is caused by this random effect. So we have an entire literature about random effect dependent on response. But recently, I'm also missing data in survival analysis, and one piece of work is we assume that we believe that the missing is actually is related to the survival time. And that time, I think that problem is the missing covariates. So some of the covariates are not measured because the patient is too sick. And therefore, we believe the missing is actually depend on the survival time. And in that situation, that's exactly the structure I have, and how do you handle the missing data in that problem. And it becomes non-ignorable because survival time is censored. The censoring is some part of missing data. It's better than missing because you have censored information. But because of the survival time is censored, the missing of covariates becomes non-ignorable. So if you have a structure of a particular problem, then I believe that it will have some probably better solution.
People on the phone, any question? Okay, so sounds like so we still have a time. So after the seminar, you can still talk with me. So okay, this is thank you for coming. Oh, another one is Dr. Charles mentioned the part 2 work. So when you have some results, let us know. We shall invite you to come back to talk about part 2, right? So today we are a little bit rush on the part 2. So we hope see you in a year.
3 years.
3 years. Should not say a year. So this is represent the very. Thank you very much.
Thank you.